The universe is a symphony of signals, light from distant stars, sound waves rippling through the air, even the complex electrical impulses in our brains. These signals, seemingly chaotic at first glance, hold hidden patterns and harmonies waiting to be deciphered. To unlock these secrets, we turn to a powerful mathematical tool, the Fourier Transform. Named after the brilliant French mathematician Jean-Baptiste Joseph Fourier, this transform takes us on a journey from the realm of time to the fascinating world of frequencies. To truly appreciate the power of the Fourier transform, we must first grasp the concept of frequency. In the simplest terms, frequency describes how often a repeating event occurs over a specific period. Think of the rhythmic beat of a drum or the regular oscillation of a pendulum. These are examples of simple signals with a single, dominant frequency. However, the world around us is rarely so simple. Most signals we encounter are complex, composed of a multitude of frequencies blended together. A musical chord, for example, combines the frequencies of multiple notes played simultaneously. Similarly, the sound of our voice is a complex blend of frequencies that gives it its unique timbre. This is where the Fourier transform shines. It acts as a mathematical prism, separating these complex signals into their individual frequency components. By analyzing the strength or amplitude of each frequency, we can gain a deeper understanding of the signal's composition and behavior. To delve into the inner workings of the Fourier transform, we must embrace the elegant language of mathematics. Fear not, for we will use intuition and visual aids to guide our journey. The Fourier transform converts a signal from the time domain to the frequency domain. It involves integrals, complex exponentials, and a touch of mathematical magic. Just as a musical score can evoke emotions, this equation reveals hidden truths about the universe. Now let's unveil the enigmatic term within the integral, the complex exponential. This term, often written as e to the power of negative j2 pi ft, is where the true magic of the Fourier transform happens. It acts as a mathematical tuning fork, vibrating at a specific frequency f. To understand this, we must venture briefly into the realm of complex numbers. A complex number consists of two parts, a real part and an imaginary part. The imaginary unit, denoted by j, is defined as the square root of negative 1. While this may seem abstract, complex numbers provide a powerful way to represent oscillations and waves mathematically. The complex exponential can be visualized as a point moving around a circle in the complex plane. The frequency f determines how fast the point rotates, while the time t determines its position on the circle. As we integrate over all time, this rotating point effectively scans for frequencies present in our signal. When the frequency of the complex exponential matches a frequency present in our signal, a resonance occurs. This resonance amplifies that particular frequency component in the frequency domain representation, revealing its presence in our original signal. Finally, we return to the integral, the grand orchestrator of this mathematical symphony. It takes the product of our time domain signal, x of t, and the complex exponential, e to the power of minus j2 pi ft, and sums up these products over all time. This process essentially measures how well our signal aligns with each possible frequency. Imagine a ballroom filled with dancers, each representing a different frequency. As our signal, x of t, enters the ballroom, it dances with each frequency, represented by the complex exponential. The strength of their embrace, determined by the product of their values, reflects how much of that particular frequency is present in the signal. The integral, like a keen observer, watches these dances unfold and meticulously records the strength of each embrace. The result is a map of the signal's frequency content, the frequency domain representation, x of f. This map reveals the hidden symphony of frequencies that compose our seemingly complex signal. Through this cosmic dance of integration and complex exponentials, the Fourier transform unveils the hidden frequencies within our signals, revealing the intricate tapestry of the universe one frequency at a time. While the continuous Fourier transform provides a powerful theoretical framework, the world of digital signals presents us with discrete signals. Instead of smoothly varying functions, we encounter signals chopped into discrete samples like snapshots taken at regular intervals. Think of digital audio recordings or sensor data collected at specific time points. To analyze these discrete signals, we turn to the discrete Fourier Transform, or DFT, the digital cousin of the continuous Fourier Transform. The DFT transforms a finite sequence of discrete data points into frequency components. It's like taking a digital photograph of a sound wave, capturing its essence in a series of pixels rather than a continuous curve. The DFT bridges the gap between the continuous world of analog signals and the discrete world of digital computation. The DFT, like its continuous counterpart, is governed by a mathematical equation, albeit one tailored for the discrete world. While the equation may appear intimidating at first glance, it follows a similar logic to the continuous Fourier transform, with summations replacing integrals and discrete indices replacing continuous variables. Let's break down the DFT equation piece by piece. We start with our discrete signal, represented by a sequence of n data points, denoted as x of n, where n ranges from 0 to n-1. These data points could represent the amplitude of a sound wave at different time intervals, the brightness of pixels in an image, or any other discrete signal we wish to analyze. The DFT aims to transform this time domain representation, x of n, into a frequency domain representation, denoted as x of k, where k also ranges from 0 to n-1. Each x of k value represents the amplitude of a specific frequency component present in our original signal. The heart of the DFT equation lies in a summation that loops through all n data points. For each frequency index k, the equation calculates a weighted sum of the data points, x of n, multiplied by complex exponential terms. These complex exponentials, similar to their role in the continuous Fourier transform, act as digital tuning forks, probing for the presence of specific frequencies in our discrete signal. Section 3. DFT in action, a world of applications. The DFT decomposes discrete signals into their frequency components, revolutionizing countless fields. From music on our smartphones to medical imaging, the DFT plays an essential role. In audio processing, it analyzes frequency content, removes noise, and compresses signals. Think of noise-canceling headphones or audio codecs for streaming. In image processing, the DFT enables compression and enhancement. Beyond audio and images, it's vital in telecommunications, radar, and scientific research. The DFT is fundamental for understanding and harnessing the digital world. Section 1. The need for speed. Enter the FFT. The DFT unlocks a universe of possibilities, but becomes a bottleneck with large datasets. Each frequency component requires summation over all data points, leading to quadratic complexity. Doubling the signal length quadruples computations, making real-time analysis impractical. Enter the FFT, a revolutionary algorithm reducing the computational burden of the DFT. The FFT exploits symmetries in the DFT, transforming it into manageable subproblems. It provides an efficient way to perform DFT calculations, unlocking the potential of frequency domain analysis. Section 2. A symphony of divide and conquer. The elegance of the FFT lies in its divide and conquer strategy. It breaks down the problem into smaller DFTs, combining them to compute the original sequence. Imagine a conductor organizing an orchestra by dividing it into sections. Each section rehearses independently, then comes together under the main conductor. Similarly, the FFT divides the input signal into smaller subsequences. It calculates the DFT of these tiny subsequences and combines them. This process repeats until the final DFT is computed. This approach drastically reduces the number of computations required. The FFT achieves a much more favorable scaling on the order of n log n. Section 3. Unlocking real-time possibilities. The computational efficiency of the FFT has been a game-changer in countless fields, empowering real-time signal processing and analysis that were once unimaginable. It has fueled a technological revolution, enabling us to interact with the digital world in ways that were previously impossible. Imagine a musician using a digital audio workstation to record and manipulate sounds. The FFT allows them to visualize the frequency content of their recordings in real time, apply filters to isolate specific instruments, or remove unwanted noise, and even synthesize new sounds by manipulating individual frequency components. This real-time feedback loop empowers creativity and opens up a world of sonic possibilities. In telecommunications, the FFT is the cornerstone of modern digital communication systems. It enables us to transmit vast amounts of data over limited bandwidth by efficiently encoding information in the frequency domain. From high-speed internet to mobile phone conversations, the FFT ensures that our digital messages travel the globe with remarkable speed and clarity. The FFT's impact extends far beyond these examples, permeating fields like medical imaging, radar technology, scientific instrumentation, and financial modeling. It allows doctors to analyze MRI and CAT scan data in real time, engineers to design more efficient radar systems, scientists to process massive data sets from telescopes and particle accelerators, and financial analysts to model complex market behavior. The FFT, in essence, has become an indispensable tool for understanding and shaping our increasingly digital world. Section 1. Echoes in Sound and Vision. The Fourier Transform shapes our experiences from noise-canceling headphones to digital photography. It compresses image data, allowing us to store and share thousands of photos effortlessly. Section 2. From Vibrations to Medical Marvels. Engineers use the Fourier Transform to ensure structural integrity, while doctors rely on it for detailed MRI and CT scans. It helps diagnose diseases and monitor treatments with precision. The Fourier Transform orchestrates technological marvels. It powers high-speed internet, financial market analysis, and even astronomical discoveries. By analyzing frequencies, it deciphers the universe's secrets. Let's tackle a pure sine wave. Represented as xt equals sine A asterisk sin, 2pft, its Fourier transform reveals a single frequency peak. This confirms the sine wave's pure tone. Now let's explore the DFT with a metronome's tick. Sampling the sound, we use the DFT to find a frequency peak at 1 Hz. This reveals the metronome's fundamental frequency. Section 3. Bridging the gap. From continuous to discrete. Sampling a rectangular pulse, the DFT analyzes its frequency content. Higher sampling rates better approximate the original signal. Section 1. Bridging the realms, time and frequency. The Fourier transform separates a signal's time and frequency components. It reveals dominant frequencies and subtle nuances. Visualization reveals hidden patterns. Transforming a musical chord shows distinct frequency peaks. This aids in image compression and medical imaging. The Fourier transform offers endless exploration. Techniques like STFT and wavelet transform provide finer granularity and adaptability. They analyze signals with transient features. The Fourier transform's impact is transformative. It aids in space exploration, medical diagnostics, and more. It empowers engineers, scientists, and musicians. The universe is a symphony of frequencies. The Fourier transform deconstructs signals, revealing hidden patterns. It will continue to drive technological innovation and understanding.